Simple ideas about FIR filters. Consider a difference equation as follows. Output y of n is equal to terms related to input, feed-forward terms, BKs, minus terms related to the output, yn minus k, AKs. Okay? In terms of AK in equation, if all terms of AK in equation 5.7 are equal to 0, then the system will be FIR, finite impulse response. Otherwise, it's called IIR. Therefore, FIR is a feed-forward system and it has zeros. All poles of FIR filter will reside at the origin. However, an IIR filter has poles everywhere in Z domain besides zeros for IIR. Right. The next topic, low pass FIR. Very simple FIR, just having two terms. H of Z is equal to 0.5 times 1 plus Z minus 1. Frequency response will be 0.5, 1 plus e to the power of minus j omega, which will be equal to cosine of 0.5 times omega multiplied by e to the power of minus j times 0.5 times omega. Okay? This term is related to the phase, having a linear phase with a slope of minus 0.5. And this term is related to the amplitude. Amplitude is even, phase is odd. Anyhow, it will be equal to 1 for omega being equal to 0 and 0 for omega being equal to pi. What does it mean? It means that higher frequencies are not allowed to pass, but lower frequencies can pass. So it's a low pass. Okay? Now, here you see the poles and zeros of FIR. You see a single pole at the origin, but it has a zero. Okay, here a zero at 180 degrees or minus 1. Okay? So when you investigate the frequency response starting from 0, okay, here when it approaches to the pi, there is no permission for passing. Okay, it means evaluating the frequency response just by looking at the pose and location of zeros. Later you will get more familiar with the idea. For instance, figures 5.2 and 3 illustrate the poles and zeros and also frequency response of the low-pass FIR filter presented in equation 5.8 respectively. Now, let's have a look to frequency response. Magnitude or amplitude, you see here, 1 having permission, but little by little it approaches to 0 when the frequency is half fs. Sampling frequency is 1000 hertz or 1k hertz. So at the maximum frequency there is no permission to pass. So it's a low pass filter. Okay, can you imagine the shape of high pass? And this is related to the phase, just linear phase. Here it jumps from minus 90 degrees to 90 degree. You are familiar with the mathematics, simple mathematics. The frequency response of the system in figure 5.8. Now, the Python code for equation 5.8 is as follows. The cutoff frequency when fs is equal to 1k hertz is computed as cutoff 250 hertz roughly. Okay, now let's go to PyCharm and run the program. Okay, the same plot. Okay, it's low pass filter and the same phase. Now, here you see a warning runtime warning, invalid value encountered in divide, because it's going to show the hospital 0 divided by 0, not a number or none. Anyhow, here we have defined how to calculate a cutoff frequency for low pass. Very simple algorithm. Okay. Here you see the numerator of the system 0.5, 0.5, denominator 1, 0. That's the story for all FIR systems. There is no denominator, or say it 1 plus 0 to the power of 0 times z minus 1 plus 0 times 0 minus 2 plus blah blah. Number of FFT samples 512. Sampling frequency 1000 hertz. And here the details. Now, cutoff has been calculated to be 250 hertz. Going back to the lecture note. Okay. You will get access to the code, so no, don't worry about it. Just scrolling to finish it up. Now, example 5.2. Use a second degree low pass FIR by cascading the above low pass filter. Okay? It means use 2 boxes of low pass filter we described. How will it appear? The transfer function will be h of z will be equal to the first one times again the second one, which is similar to the first. Okay, doing little mathematics will be 0.25 times 1 plus 2z minus 1 plus z minus 2. Now here you see 2 poles at the origin and 2 zeros at 180 degrees, or z equals to minus 1. Okay? So we want to investigate the effect of having a second order low pass filter. Figures 5.4 and the next illustrate 5.5 illustrate the poles and zeros and also frequency response of the low pass FIR filter presented in equation 5.9 respectively. Here you see the magnitude. Okay, similar but somehow different. Here you see the cutoff will be smaller. Now, take home. Change the above program to realize equation 5.9. The cutoff frequency should be about 182. You see, a decrease in cutoff frequency, a better shaping of transition region. That's the effect of the degree of the filter. Okay? Please think about it. Explain how the cutoff frequency is reduced by decreasing the order of the filter. Also add a new part to the program to find the zeros and poles of the new system. Okay. Now, high-pass filter. Simple ideas about high-pass FI. You see here, similar to low-pass but with a minus. So, h of z is equal to 0.5 times 1 minus z minus 1, or frequency response will be, I don't want to repeat them, just leading to 0 for the lower frequency, but 1 for the higher frequency. Okay? Now, lower frequencies have no right, no permission to pass, but higher frequency can pass. So it's high pass, isn't it? It can be concluded that the matched high pass and low pass filters are related as h high pass of z is equal to h low pass of minus z. Is it by chance, or it every time it happens for any degree, any type of high pass and low pass? It means that wherever you see z in low pass filter, just change it to minus z and it will lead to a high pass. And that's a great idea, isn't it? Anyhow, poles and zeros for high pass FIR, you see here, the pole is at the same location, origin, but the zero has come to 0 degree, or z equals to 1. Okay? So for lower frequencies, there is no permission because they will be multiplied by 0. Okay? Now, two figures illustrate the poles and zeros and also frequency response of the high-pass FIR filter presented in equation 5.10 respectively. Here you see the frequency response. You see here higher frequency, which is 500 half sampling frequency, okay, has permission to pass, but lower frequencies cannot pass. This is the phase of the system linearly. Now, provide similar review for high pass filter 2. Okay. It means we need coding in Python and discussion about what is going to happen. No, simple idea about band pass FIR. It's obtained by connecting the low pass and high pass filters in series or cascade. Okay, here you see the first part is related to low pass and the second part to high pass. So you are cascading low pass followed by high pass. It will result in 0.5 times 1 minus z to the power of minus 2. No term for z minus 1. Okay? Or h of omega will be j times sine of omega times e to the power of minus j omega, which will be 1 permission to pass for middle range of frequency. but low and high frequency cannot pass. So it's band pass. Okay? Think about the idea. Moreover, think about the amplitude and phase of the system. J means pi over 2 plus a linear phase here. And this part is related to amplitude. Anyhow, poles and zeros of the system, we will have two poles at the origin and two zeros at the location I am mentioning. Z equals to 1 and Z equals to minus 1. Real zeros. Okay? Two figures illustrate the poles and zeros and also frequency response of the bandpass FIR filter presented in equation 5.11 respectively. Now let's have a look to frequency response. Here you see 0 and pi, or in frequency range 0 and half fs cannot pass, but middle range can pass. And this is the phase. Don't worry for phase. For instance, the following Python program finds two cutoff frequencies. You see, going back to Shay, we have two cutoffs. Here, very clear. You see here, cutoff, the first one, and the second one. Do you remember cutoff frequency, the definition of cutoff frequency? Okay. Maybe some people will ask, here we see 4 cutoff, but remember that we should always discuss from 0 up to half fs. This is the mirror. To have a complete and whole figure, we have added it to figures. Otherwise, it suffices to present from here up to half fs. Okay. The following Python program finds two cutoff frequencies at the first one 121 and the second 375 and plots the frequency response. Now, we will run a bandpass filter program. Okay. Here you see the idea, similar plot. And cutoff, the first one is 121 and the second one is 375. And here you see the algorithm for finding two cutoffs. Find cutoff for bandpass. How it's done. Very simply, you may find it. Later, you'll get access to the code. Okay, so scrolling very fast to keep the length of the video as short as possible. Now, take home 5.5. Do similar investigation for bandpass filter. Moreover, find the stop-band frequencies fs1 and fs2 for a given attenuation. Okay? Every time you need to improve the coding presented as lecture notes. Now, band stop FIR. If cosine is used instead of sine in equation 5.11, the result will be a bandpass filter. What does it mean? This time we have started from frequency response, h of omega is equal to cosine of omega times e to the power of minus j omega, which will be 0 for omega being equal to pi over 2. Middle frequency has no right to pass, but is equal to 1 for omega being equal to 0 and pi. The reverse idea presented for bandpass. Okay, that's a tricky play with cosine and sine. Okay, now if that's the case, so we can write h of omega is equal to 0.5 times 1 plus e to the power of minus j 2 omega, or leading to transfer function 0.5 times 1 plus z minus 2. Okay. Here you see the location of poles again at the origin, 2 poles at the origin. It is the story for all FIR systems. There is no active poles, but the 0, the first one is at 90 degree over unit circle. The next one is at minus 90 degree, or the location is z is equal to plus minus j, imaginary part. There is no real part for the zeros. Okay. Similar idea, pole zeros have been illustrated. What about frequency response? Here you see the middle range frequency has been notched, has no right to pass, but low frequency and high frequency can pass. And this is the phase. Take home 5.6. You know what to do about band stop filter. Now, another type of filtering, all pass FIR. It is of the form h of z is equal to z to the power of minus n. You see here, the amplitude is 1 times z to the power of minus n. So, for any frequency, the amplitude will be 1. So, permission for all frequencies has been granted.